Hello everyone, today let's take a look at QP139. We're doing some order stats now, so let x1 all the way up to xn be independent random variables, each uniformly distributed between 0 and 1. So part A, what is the expected value of the maximum of just 3 of these random variables, x1, x2, and x3? So if we let z be this maximum, well, x1, x2, and x3 are all distributed uniformly between 0 and 1. So for instance, x1 might be right here, and then maybe x3 might go right here, and then maybe x2 was over here. They're all placed independently somewhere on this line, everywhere with equal probability, and in this case, the maximum of these 3 would be x2. So in part A, we want to find the expected value of z. So z is continuous random variable. We know the definition of expected value. The maximum could be any point between 0 and 1, right? So it's going to take values from 0 to 1 of z times basically the probability that z is equal to little z. But in the continuous case, you're supposed to basically write this as f sub z of z, the density function, but basically they mean the exact same thing, essentially. So now we just have to find this probability distribution, the density function of z. And again, for all intents and purposes, this is just the probability that z is equal to little z. I think this way makes it more intuitive. Okay, so let's figure this out, right? If I have some point z, I know my maximum is going to be somewhere between 0 and 1. Let's just say it's right here. Now, z is the maximum of x1, x2, and x3, so this must be one of those 3 values. So because z is going to be one and only one of either x1, x2, or x3, they fully partition our sample space, so we can use law of total probability, essentially. So for our first case, let's just assume that x1 is our maximum, right? So x1 takes this value of z, so what is the probability of that? Well, that's just basically going to be the density of x1 at the point z. And in order for x1 to be the maximum at the point z, we need basically x2 and x3 to both fall before z. Well, because all these variables are independent, given that x1 is equal to z, the probability that x2 and x3 both fall before z are just going to be basically the probability that x2 is less than z, and then we can just multiply these because they're independent, right? The probability that x3 is less than z. So this right here is basically the density of the maximum being x1 at the point z, and now with x1 doesn't have to be the maximum, right? It could also be x2, and in that case, well, it would be disjoint, so we add on basically the density of x2 at the point z. And then again, in that case, x1 and x3 would both have to come before x2. They're all independent, so we multiply basically the probability that x1 is less than z times the probability that x3 is less than z. And then finally, our third case is going to be the same, right? If x3 is now the maximum at point z, so we have this density, f of x sub 3 of z, and they're independent, so we multiply that by the probability that the other 2 are before z, so x sub 1 and x sub 2 being less than z. And again, all the x variables are identically distributed, so like basically this is going to be the exact same as this, which is going to be the exact same as this. So we can just basically rewrite this as 3 times basically f sub x in general of z times the probability that x is less than z basically squared. And the density of a uniform between 0 and 1 is just going to be 1. And the probability that x is less than z if we're distributed from 0 to 1. So we basically have 0 and 1 here, and z is some arbitrary point where our density is just 1 up here. Well, we're just going to basically calculate the area under this. It's just going to be z times 1. So it's just going to be z, right? The probability that x is less than z is equal to z, and this density is 1. So we can just rewrite this as basically 3 times z squared. So that right there is the density function of the maximum. And now all we have to do is just plug that into our expected value formula and solve this integral right here, and then we should get the expected value of the maximum, which is what we were trying to solve. So this is going to be from 0 to 1 of z times basically 3z squared dz. So that's just going to be the integral from 0 to 1 of 3 times z cubed dz, which is just going to be equal to 3 on 4 times z to the power of 4 evaluated from 1 to 0, which is just equal to 3/4. So if I place 3 values randomly on a number line between 0 and 1, the expected value of the maximum one is going to be 3/4, which makes sense. It should be greater than 1/2. Now, an even easier way to solve this would just be looking at the CDF of z. Z is the maximum of 3 uniformly distributed random variables. So the CDF of z is just going to be the probability that z is less than or equal to little z. So basically what we're saying here is that when we look between 0 and 1 and we fix some z value, we're just saying what is the probability that the maximum is before this z value? Well, it's just going to be equal to basically the probability that all 3 are before that z value. And because they're all independent, this is just the same thing as the probability that x is less than or equal equal to z, x1 in fact, times the probability that x2 is less than or equal to z, times the probability that x3 is less than or equal to z. Now again, for a given one of our x's, they're all going to have a PDF of 1, right? So the probability that x1 is less than or equal to z is basically just the area right here. It's just equal to z times 1. So z, the probability that x2 is less than or equal to z, well, x2 is identically distributed as x1. So it's also going to be z, and so is x3. So it's just going to be z cubed. And then to get the PDF of z, all we have to do is just take the derivative of that. So it's just going to be 3z squared, exactly what we got before. And then you could again take the integral that we just did and you get 3/4 again. Another way that you could do it is by using the tail sum formula, which we proved all the way back in QP 122. And yes, it still works for continuous random variables. If you wanted to use tail sum, well, we know that the probability that z is less than or equal to some little value of z is going to be z cubed. So basically the probability that z is greater than or equal to z, or greater than z, it doesn't matter for continuous, is going to basically just be 1 minus z cubed. Sorry, this should be a cube here. Then again, we can just tail sum this like we did in QP 122. We're just going to take the integral from 0 to 1 of the probability that z is greater than z. We know that that's going to equal the expected value of z, again from QP 122. We plug in this right here. We get basically the integral from 0 to 1 of 1 minus z cubed, obviously with respect to z. And then we can just take this integral right here. That's just going to be equal to 1. And then when we take the integral of negative z cubed dz, it's just going to basically be z to the power of 4 divided by 4, evaluated from 1 to 0, which is just equal to 1/4. So we get 1 minus 1/4, which is 3/4. Again, the exact same thing that we got in the previous parts. Okay, so now in part B, it shouldn't be too hard once we've done part A. In general, what is the expected value of the max of n different x1s and the minimum as well? So let's start with the max. Let's again let z be the maximum of x1, x2, all the way up to x sub n. Let's start this time by doing the CDF trick because that is going to be the easiest. Let's just take the probability that z is basically less than or equal to little z. So again, here, if we have a number line between 0 and 1, we pick some z value. What is the probability that every single one is going to be less than that value? Now, for a random uniform 0 to 1 variable, the probability that it's less than z, again, it's going to have a PDF of 1, is going to be the area under this curve. It's just going to be z times 1, so z, but we have n of them and they're independent. So the probability that all of them are less than z is just going to be z to the power of n. Now we can differentiate this to get our density is just going to be equal to n times z to the power of n minus 1. And then to get the expected value of z, where z is the maximum of all these, we're going to integrate over all the possible values that z can take. So anywhere between 0 and 1 of its density, which is n times z to the power of n minus 1 times z, right, dz. Now in here, this is just going to basically be z to the power of n dz. We take the integral of this, we just get n, which is a constant, times z to the power of n plus 1 divided by, let's see, n plus 1, and we're evaluating that from 1 to 0. When I plug in a 1 for z right here, I just get 1 on top, basically, and then I have n on n plus 1 as my constant. So when I plug in 0, I get 0, obviously. So this is just going to be my final answer right here. So the maximum of n uniformly distributed 0 to 1 random variables is going to be n on n plus 1. And that makes sense when we plug in our values from up here. We had 3 uniformly distributed 0 to 1 random variables. So when we plug in n equals 3, we again get 3/4, which is exactly what we got in part A. So this is the general form of that. And again, you could also get this by doing the tail sum of integrating 0 to 1 of 1 minus z to the power of n, basically dz, right? In that case, this would just integrate to basically 1 minus z to the power of n plus 1 on n plus 1, evaluated from 1 to 0. So it's just going to be 1 minus 1 on n plus 1, so just equal to n on n plus 1, same thing we got right here. And you can also construct this PDF in the same way that we did in part A initially. So okay, now let's move on to finding the minimum. So let's let y basically be the minimum of x1 all the way up to xn, and let's see how we can do that. So again, to find the expected value of y, all we want to do is just integrate from 0 to 1 the possible values that y can take of y times basically its PDF, which we need to find, right, dy. So again, I can use a similar trick. I know it's going to be easy to find some type of CDF for this, and then basically all I have to do is differentiate that to get my density. So if I fix some value of y between 0 and 1, it's going to be very easy to calculate the probability that all of these come after y, because in this case we want y to be our minimum, so we want to calculate the probability that all of them come after y. So how do we do that? Well, first of all, because they're all identically distributed, let's just look at it for a general x. They're all identically distributed with a uniform between 0 and 1. So this PDF for a random x is going to be 1. So now what's the probability that it comes after y? Well, it's just going to be the area right here, which is basically, well, this distance right here is 1 minus y with a height of 1. So basically the area is just going to be 1 minus y. So this is the probability here that one of our x variables comes after y. Now we can kind of easily find the probability that the minimum is greater than or equal to y. Because all of these are independent, the probability that the minimum of them is greater than or equal to y is just going to be equal to the probability that all of them come after y. Which again, because they're independent, is just equal to basically the probability that one of them comes after y multiplied by itself n different times. And this probability right here we just calculated was 1 minus y. So this is just going to be 1 minus y to the power of n. Now, since this is already basically in tail sum form, the easiest way to solve this is just going to be use the tail sum formula from 0 to 1, basically of 1 minus y to the power of n dy. This will be our expected value of y. So taking the integral of this, well, basically what I'm going to do, take the antiderivative of this, is just going to be negative 1 minus y. Whoops, my y went away here. 1 minus y to the power of n plus 1 divided by n plus 1. It's going to be evaluated from 1 to 0. When I plug in y equals 1, I get 0. So 0 minus basically negative, and now when I plug in 0, I'm going to have 1 on top, and I'm going to have n plus 1 on the bottom, and then these negatives are going to cancel, and I'm just going to be left with 1 on n plus 1. So this right here is the expected value of the minimum, right? The expected value of y is 1 on n plus 1. So this also does make a little bit of sense, because basically what we're saying is as we increase n, as we add more and more basically random variables between 0 and 1, the expected value of the minimum is going to get less and less, because we're more and more likely to get one that's small, right? And again, other ways to solve this as well, you could have just differentiated this to get the PDF and then done the expected value formula by plugging the PDF into this right here. You would have got the same answer, or you could have constructed this PDF in the first place, basically the way we did it first of all in part A. Okay, so now finally for part C, the most general case for general independent random variables, not necessarily uniformly distributed between 0 and 1. They could be of any distribution, right? y1 to yn. What are the expected values of the maximum and the minimum of these? Okay, let's start by looking at the maximum. And this is very general, but we can use the same trick. So z could take basically any possible value, right? We're not restricted to basically 0 and 1 now. But still, if we fix some little value of z, there's still independent random variables, right? We can use the same CDF trick. So here I fix some value of z, which we want to be our maximum. So what is the probability that all of our variables y1 all the way up through yn basically come before z? So more formally, all we're doing here is we're taking z, which represents the maximum of all these random variables, and we're saying what is the probability that it's less than or equal to some fixed value of z. And then since we know that the maximum being less than or equal some fixed value is exactly the same as all of them being less than or equal to some fixed value, and since they are all independent, here's what we can do. Well, the probability that y sub 1 comes before z, well, that's just basically the CDF of y sub 1. So f of y sub 1 of z. Now the probability that y sub 2 also comes before z, since they're independent, we can just multiply them. F sub y2 of z right here, the CDF for y sub 2. And etc., right? We're just going to end up basically multiplying every single one of these CDFs. So all we have to do is basically take the product, right? Because we're multiplying stuff from basically I equals 1 all the way up to n of the cumulative distribution function of y sub I of z. If these were all identically distributed, then they'd all have the exact same CDF. So we could just say in that case that we're just taking f sub y of z basically to the power of n. So in the case when they're identically distributed, this right here would basically be the CDF of z, the probability that z was less than or equal to little z. And then we could differentiate this just to get basically, well, what would we get? We get the PDF. So the PDF of z, f sub z of z, is just going to be equal to the derivative of this, which we can just use a little chain rule action. We have n times the derivative of this inside here, which is just going to be the PDF of one of our random variables y at the point z. And then we need to multiply that by basically f sub y, the CDF of y at the point z to the power of n minus 1. And again, this right here is basically like saying, okay, we fixed a z value. Let's say we fixed our z value right here. Well, the probability of that being our maximum is first, basically, let's look at y1. If y1 is our maximum, it's going to be at that point with density f sub y of z. So that's this term right here. And if that's our maximum, then every single other point has to be less than z. So that's all these points right here. The remaining n minus 1, since they're are all independent, we're multiplying them, and we're multiplying the probability that they are all less than z. And that was when we just looked at y1 being our maximum, but if we looked at y2, we'd get the exact same thing. So that's why we sum up n different times. They're all identically distributed, so they're all going to have the same distribution. So that's why we have this n out front, right? So that's every term within this equation and what it means, but we just use the CDF trick, which makes it easier. So this right here is for identically distributed independent variables. What is the maximum? It's this right here. This is going to be our density, right? So the expected value of z is just going to be basically the integral over all possible values that z can take. In this case, it's arbitrary, so we'll go from negative infinity to infinity of basically z times f sub z of z, and basically that will be our expected value. Obviously, this right here is where this is basically our probability distribution right here, and there's no way to simplify this further without basically knowing like what the underlying distributions are, right? So it's just going to be, this is our expected value right here, and this is the distribution of basically the maximum. Now again, exact same story for basically the minimum. Let's have a be basically the minimum of y1 all the way up to yn. Actually, let's just have this be x. So if x is the minimum, right, it's going to be somewhere down here, the minimum out of all of our variables. So we have, maybe it's y2, and then maybe we have all the other ones basically some point ahead of it. And again, they're all identically distributed. So my probability density function for basically, let's say x now, f sub x of x. Well, again, I can cycle through every single point, right? If I have y2 as my minimum, so the density of y2 at that point is just going to be f sub y2 of x. Then if we fix one of our points, y2 at the point z, then the probability that it is the minimum is going to be basically the probability that all the other ones come after. And that probability, since they're all identically distributed and they're independent, again, it's just going to be the probability that basically y is greater than or equal to z, or greater than z. It doesn't matter for continuous, right? And then that's going to be raised to the power of n minus 1. So for the CDF, you usually write it as f sub x of x is just going to be equal to basically the probability that y is less than or equal to z. So basically this right here is just going to be 1 minus that CDF. So we're just going to take 1 minus f sub x of x, where f is capitalized, that means CDF, and when it's lowercase, it's a PDF. This actually should have been f sub y of x, but this is our equation right here when we fix y2 at the point z, but we still need to do it for every single one, right? So if y1 is instead the minimum, then we're going to get this exact same thing, right? They're all going to be f sub y of x times this, so we have n of them, so we can just multiply this by n, again, because they're independent and identically distributed. So these right here are the general cases. If you wanted to find the expected value of the minimum, all you do, again, the expected value of x is just going to be equal to the sum over all possible values in that x can take. In this case, it's arbitrary, so we'll go from negative infinity to infinity of x times f sub x of x, the PDF of the maximum, the minimum, and with respect to x, and that's just going to be this right here. You could have also used the same CDF trick, but I think you get the point at this point, right? So yeah, this right here is basically most of what you need to know about order statistics, right? We did a lot of stuff in this one problem. It had 3 different parts. It's pretty long, but basically you got the idea.